What's up, everybody? Mr. Kozad here to go over lesson 2.6 for pre-calculus. This lesson covers polynomial inequalities as well as rational inequalities. So I'm going to do kind of an abridged version of the lesson. I'm going to give you a couple of examples from each different type because the process here is super similar. So the first problem that we're going to do here is solve x squared minus 8x plus 16 is less than or equal to 1. Okay, the first thing we want to identify here is we want to try to get this equation to be less than or equal to 0. So we're going to take this 1 and we're going to move it to the other side. So let's just simply rewrite it to x squared minus 8x plus 15 if we subtract the 1 on both sides. Now that's less than or equal to 0. Okay. Now from here what we're looking for is we're looking for all x values that make this equation less than or equal to 0. So if we think about that in the context of a graph, that would be asking us where on the graph is the function below the y-axis, or the x-axis, I'm sorry. So if you think about this, if this is our x and our y, wherever this function is less than or equal to 0, we're looking for anything that's below the x-axis. In other words, anything that has a negative y value. So that's the region that we'd be looking for. Okay, but obviously our inequality here is only talking about the x values. Okay, so here's what we're going to do. We're going to think about this in the context of a number line. And to find my x-intercepts, if you will, this is just looking at the x-axis. If we find our x-intercepts, we factor this. So we're looking for two numbers that multiply to give me 15 and add up to negative 8. So that's minus 5, minus 3, less than or equal to 0. And then we solve each one of those. And again, my two x-intercepts are x equals 5 and x equals 3. I know I said those backwards, but I'm going to arrange them appropriately on my x-axis. Now, the next thing that you're going to decide is, do these points, these x-intercepts, get open circles or closed circles? And we tell that by looking at our inequality symbol. Since it's an or equal to, we're going to put closed circles at each one of those points because we are looking for or equal to. It can equal 3, it can equal 5. So then the next thing that I would look at here is I would look and say, okay, this is a quadratic function that's going to be the shape of a parabola where its two x-intercepts are 3 and 5. And I look at the lead coefficient, and I notice that the lead coefficient here is positive. So that means that one possible graph for this would look something like this. Okay? Now the reason that I showed it this way is, remember what we talked about originally. I'm looking at this function for any x value that makes this function equal a negative value. Okay, so I'm really looking for anything in this region here because this is the part of the graph that is below the x-axis. In other words, this is the part of the graph that gives me negative y values. So the way that I'd write that is I can do any x value between 3 and 5 would give me a negative function value. Okay, so what we can do there is now we can write this in interval notation, parenthesis 3, comma to parenthesis, bracket 3 to 5 with the bracket. Remember, we use brackets when it can equal that number, closed circles, and we would use parentheses if it were open circles or it couldn't equal that number. Okay, now some of you may be really confused by that whole graphing concept because you're like, Kozad, we're just talking about x values. Why are we graphing it and talking about y values? Well, another strategy for the same question is you could have gotten your x-intercepts the same way, okay? Closed circle, and you could make what's called a sign chart, which basically determines whether or not a section of this number line gives you positive values or negative values. So after I factored that, I had x minus 5 times x minus 3 less than or equal to 0. And what I'm going to do is I'm going to pick a test point in each one of these regions here. So something less than 3, I'm going to use 0. Something between 3 and 5, I'm going to do 4. And something greater than 5, I'm going to just do 6. And I'm going to test those points. Okay? So I'm going to test those points and see what happens. So when I plug a 0 in for x, I get 0 minus 5 is negative 5. If I plug a 0 here, I get 0 minus 3 is negative 3. So that would be negative 5 times negative 3. Well, a negative times a negative is going to be a positive. Okay? So in other words, a positive number is not less than or equal to 0. So we would say that that section does not work. Same thing, we can plug in our 4. So 4 minus 5 is negative 1. 4 minus 3 is 1. So negative 1 times positive 1 does give me a negative in that region there. So anything between 3 and 5 gives me a negative value. And that section would work on this original inequality. Same thing with 6. 6 minus 5, positive 1. 6 minus 3, positive 3. A positive times a positive is always positive, which would not work because we want to be less than or equal to 0. So if you make a sign chart like this, you can look and see pretty clearly that we're between 3 and 5 as well. Two different ways to skin that same cat, so you got to pick a way that works best for you. Okay, let's try another one. All right, so this one's similar but a little bit different. Here what we have is we've got a polynomial function that's to the third power, and we have a really important hint here. This hint is that negative 2 is a factor. Okay, so if we translate that to a binomial, that would be x plus 2 times something. So let's see what we have left over if we factor that out. So you have to go back to some algebra 2 here and remember that if negative 2 is a factor, we can divide using synthetic division and see what we have left over. Okay? So again, with synthetic division, we just deal with the coefficients. We bring the first coefficient down. 3 times negative 2 is negative 6. We add those to get negative 13. Negative 13 times negative 2 is positive 26. 26 plus negative 22 is 4. 4 times negative 2 is negative 8. And we should not be surprised to get remainder 0 because we were told that negative 2 is a factor. So here's where we're at. We know we have an x plus 2 that's a factor. And now what we have left over is we have a 3x squared minus 13x plus 4. And that's strictly less than 0. So now what we can do is we can take this trinomial here and we can try to factor that. Now depending on your method of factoring, it's kind of up to you how you do that, but this pretty clearly is going to factor, however you do it, to x minus 4 times 3x minus 1. Again, I went through that pretty quickly, and I'm not going to show you. The purpose of this lesson isn't to teach you how to factor. If you need help with that, you can come and talk to me about it, or there's some other videos that you can look at for factoring. But here's where we get to. So now what we can do from here is I'm going to show you both ways. I'm going to show you the way where we can think about it graphically, and then the way to make your sign chart. So there's going to be 3 x-intercepts here. There's going to be one at negative 2. There's going to be one at 1/3. And there's going to be one at 4. Then ask yourself, on those x-intercepts, are you going to use open circles or closed circles? The correct answer there is open circles because this is not an or equal to inequality. Okay, so then what you can do is you can think about what the shape, the general shape of a third degree polynomial looks like. Okay, a third degree polynomial is going to be kind of S-shaped, and the ends go in opposite directions. The ends go in opposite directions. So if I take the general shape that I know from Algebra 2 and apply that to the graph that I have, or the x-intercepts that I have, the graph could look something like this. That goes up to the right. I know it goes up to the right because I have a positive lead coefficient. Well, then if you look at the graph this way, and you know that you want the function values to be less than 0, you're looking for anything here that's below the x-axis. Okay, so that would be this region right here would work. Between 2 and 1/3 does not work because those values are actually greater than 0. 1/3 to 4 would also work because, again, those values are negative. And then 4 to infinity would not work because these values here on this part of the graph are greater than 0. Okay, so we have two different parts here, and we're going to write the union of two inequalities. So this first part will go from left to right. We go from negative infinity all the way up to 2. And make sure you use a parenthesis because you have an open circle. And that's going to be the union of 1/3 to 4. Again, please use a parenthesis there. Let me clean this up. Please use parentheses there because you cannot use any of those x-intercepts because it's not or equal to. So this is what your answer would look like. Now, if you don't like that method and you were a bigger fan of the sign chart, you're going to start with the same number line with the same critical points. Okay, open circles on all of them. And you're going to pick a test point in each region to test. So I would do like 0. I would do, oh, that's a -2. Sorry about that. -2. I missed that. Yeah, make sure you check that. That should be -2, but you're smart enough. You probably already figured that out. So number between -2 and 1/3. So I got to change this one. I'm all messed up now. Okay. So I've got to change this to, let's try maybe -3. Get rid of that. Need the pen. Let's make this -3. We can make this 0. And let's make this 1. And we could try 5. And again, what you would do is you'd take those test points and you'd plug them in right here. And you'd determine if you got a positive value or a negative value. Okay, and what we'd be looking for there, so that if you use -3, you'd get a negative value. If you used 0, you'd get a positive value. If you used test 1, you'd get a negative value, which works for us. Okay, a negative value. And then if you used 5, you'd get a positive value, which would not work. Okay, and again, what we're looking for there is we're looking for the regions that give you negative values. So again, same conclusion, just a different way of thinking about it. So it's up to you which way you like the best. Okay. All right, so here is an inequality that has some unusual solutions to it. Okay. So what we can do with unusual sets is the same kind of concept. We're going to factor these. The problem here is that x squared plus 2x plus 3, that does not factor. Okay, it can't be factored. So we'll have to go to quadratic formula to try to find the zeros. So we have -2 plus or minus the square root of 2 squared, which is 4, minus 4 times 1 times 3, all over 2a, in this case is just 2. So let's clean that up. We get -2 plus or minus the square root of 4 minus 12, that's -8 over 2, which if we clean that up, we'll end up getting -1 plus or minus I root 2. Not root 8, root 2. Again, if you're unsure how we simplified that, there's another video for you for that. But we should get to here. Okay, so we see imaginary x-intercepts. So I know that if I graph this parabola, it would not cross the x-axis. It would not cross the x-axis. In fact, it's going to open up. And I know it opens up, again, because if I look at the lead coefficient on the x squared, it's positive, which means it opens up here. Okay, so if this part A is asking you where is this expression less than 0, and you look at the graph, well, clearly you can see from the graph that function is never below the x-axis, so it actually never has values that are less than 0. So for part A, we would say that there's no solution. But see what happens when we switch to B. We can actually change that. So now we've changed it to greater than or equal to 0. And if you can use this same graph, and you see, well, it's actually always greater than or equal to 0. So here we would say all real numbers, or we would write it in interval notation, -infinity to positive infinity. Okay? All right, here's another special case. Another special case. Solve x squared plus 12x plus 36 is greater than 0. Okay, so you obviously want to try to factor this. And this is a special case because you get the same factor squared. You're going to get x plus 6, the quantity squared. Well, what we should know about the graph of this function is that it does have one x-intercept. It has an x-intercept at -6. This parabola is going to open up because it has a positive lead coefficient. It's going to be an open circle because it's not or equal to. So this graph, if we graphed it, is actually going to bounce off the x-axis at x equals -6. So then if we're looking at the graph and we see we want the values that give this expression positive values, we're looking for anything above the x-axis, which as you can see is all real numbers except for this open circle at -6. So here's how we're going to represent that. We can go from -infinity to -6 with a parenthesis, and we're going to take the union of -6 to positive infinity. So in other words, this is basically saying you can use all real numbers except for -6. Now look at what happens here on the next graph where we change that sign to or equal to. So we can use the same graph, But now what's changed here on that graph, I don't need the y-axis, is that we can be equal to 0. So now at -6, we can close that circle. So clearly you can see by this graph there are never going to be x values that give you a value that's below the x-axis. So this is never going to be less than 0, but we have one case where it can actually or equal to 0. So our solution here would be just a single number, -6. That's the only value that makes this inequality true. So for part C, we had all real numbers except -6, but when we flip the sign around and make it or equal to for part D, there's exactly one solution that works for that. Now in this graph, what we have to do is we have to think about the nature of these multiplicities of these zeros. Okay, so this is actually factored for us, so that the hard work's done. So I've got a intercept at -2. I've got an intercept at +3, and I've got an intercept at 6. Now these powers signal us the multiplicity of those zeros, okay? And if we think about this, okay, if we add the powers together, so that be x to the third, x to the third, x squared, that's going to end up being a x to the third, x to the sixth, x to the eighth. Okay, so this will be an even degreed polynomial, okay? So it's going to have a W-shaped graph. It's going to have a W-shaped graph, okay? And the multiplicities here are, if you have an odd, we're going to snake through that 0. If you have a even, it's going to bounce off that 0, okay? So I see odd multiplicity, even multiplicity, okay? So what we're going to do is we're going to come down and we're going to snake through -2, snake through it. And then we're going to make a turn somewhere and we're going to snake through the 3. But then watch what happens here. We're going to bounce off of 6. We're going to bounce off of 6 and go off in the same direction. Okay? So this is a rough sketch of what this would look like. And obviously, I should have done this first, but we need to put open circles on each one of those x-intercepts because it's not an or equal to inequality. Okay? All right, so what we're looking for here is we're looking for all the regions where this function is positive, so every region that's above the x-axis. So here I see a region right here that's above the x-axis, and I also see a region right here that stays above the x-axis. Okay? Now we have to be really careful with this point here. We're going to actually have to write the union of 3 separate inequalities. So the first one's pretty easy. It's from -infinity to -2 with parentheses. The second set is I start at 3 and I go to 6, but I have to split this into 2 because remember 6 is an open circle. It can't equal 6. So I go from 3 to 6, and then my third inequality is then I go to from 6 to infinity. Again, you might be confused on why we have to split that into 2 different inequalities, or 2 different parts, and the reason is open circle at 6 means 6 is excluded. If you just wrote it from 3 to infinity, you would be saying that 6 is allowed to be used, and clearly we can see open circle at 6 means it cannot be used. Okay, so that's it for this one. We'll come back and we'll do rational inequalities later.